In 2012, Sean Parent gave a talk titled C++ Seasoning, where one of the key themes about that talk was about refactoring code and how we should be avoiding raw loops in favor of algorithms and content that can really describe what you're looking at trying to achieve with your code rather than how you're trying to achieve said computation. And so I'm going to take you through a bit of a journey and how we can capitalize on that 7 years down the track and see what's changed. One big thing that's changed is we've now got a new set of overloads for the standard algorithms in a brand new namespace, as well as a whole bunch of new abstractions that allow us to compose our ranges a lot more effectively. And so that leads to people wondering if we are going to be doing away with iterator-based overloads for the most part, or if iterators are going to be something that are just old things now. And so what we'll do is we'll start out with a motivating use case for iterators, followed by what iterators are in a bit more rigor, but not too much rigor. Then we'll look at strings as they are in Rust, and then we'll take a look at a HackerRank problem that talks about fraudulent activity notification. If you want to ask questions, I will intermittently stop, so feel free to interrupt me at those points. So let's start off with a motivating use case. When I was 6 years old, there was a TV show, you might have heard of it, it's called Pokemon. At the halfway point of the TV show, there was this thing called Who's That Pokemon? And it would show this silhouette of a Pokemon, and you'd have to try and guess it before the commercial's finished. So we're going to play What's That Algorithm? So I'm going to give you a moment to digest this, and you're going to have to let me know what algo is.
Search.
What kind of search?
Find.
Find is the name of the algorithm, yes. What kind of computation are we doing here? Linear search, yes. So sorry, what was your name again? Yes. Sorry? Vlad. So as Vlad was saying, it's find. And specifically, it's a find for a vector of t. And this is what a find looks like for an array of t and of size n. And this is what it looks like when we have a find for a reference to a C-style array of size n, followed by a pointer to an array of size n. And we can kind of summarize all of this up in C++20 using span, because span is a nice convenient way to say I have a contiguous sequence of elements of some size. And so now we just have one nice convenient way to refer to all of them. But what's the problem with this particular implementation of find? I did give a bit of a hint in my explanation on what span is. What if it's not contiguous, such as dec? Dec has basically the same syntax. So now we have two overloads that look almost the same. But this isn't the only kind of data structure that we have. We also have singly linked lists, which look like this. And we have doubly linked lists, which look like this. For those who didn't quite catch it, the code is almost identical save for the type. So I got one question, one burning question. Does anyone else have a question at this point about the code that I've been displaying? Doesn't it all look the same? Does anyone disagree with that statement? The code all looks the same? Okay, no disagreement. So let's quickly run through what we have. We have a find function. We've got two overloads here, one for span because I'm not going to talk about any of the other contiguous memory ones, and the linked list one because that's really the more important one as opposed to dec. So what we're doing is we have a return type which gives us some predefined information, and we're going to consistently look through that sequence of elements until we reach some sort of pre-agreed stopping point. Now, for that stopping point is really irrelevant. It's mostly to say this is where we have no more elements left to look through. And then we're going to go and find the successor of said element, and we're going to use that in the next iteration. And then inside the body of the loop, what we're going to be doing is we're going to query the current value and see if it's equivalent to the value that we have provided that we are looking for. And if it is, we'll return the position of that element. Otherwise, we'll continue looking, and once we've exhausted the sequence of elements, we'll say that we return some predefined value that indicates, no, this is not in the sequence of elements. Does anyone have any questions at this point? No? Okay, good. All right, what about streaming data? Because we can do a linear search on streaming data as well. It's not quite a one-to-one analogy, but this is what, given the previously mentioned code, this is what a linear search might look like for streaming data in linear search fashion, where we pass in an iStream and we continue to take data until it matches our looked for value, or we run out of things to take from the stream. And then if we've got something, we'll return it along with the stream. Does anyone have any questions on this slide? No? Cool. Oh, have I? Oh, indeed I have. That was meant to be a T. Oops, my bad. All right. So we have iterators, which are the answer to making all of this look a little bit more uniform. And that means that we have less code to worry about, which means that our implementations will be simpler, and we won't have to actually have as much of a headache when things go wrong. And simultaneously, if we want to support more users, they don't have to make requests for us to support them. They can follow our interface, and then they'll be able to be supported by Find as well. Now, an iterator is a generalization of a pointer, which means that all pointers are iterators, but not the other way around. And that means that we can look at using iterator syntax to refer to elements. So this table demonstrates what the differences are between a span, a linked list, and how an iterator addresses this problem. So with span, we have an index, and that index is used for reading and writing. Is used through a subscript operator. And for linked lists, we have a pointer to a node where we dereference the iterator and take its data. And for an iterator, we are just simply dereferencing it. And then for the successor, which is the next element, for the span, we are increasing the integer that is its index by 1. For the list, it's going to take the next element, which is referred to by the node structure itself. And for the iterator, it's just going to be a single ++i. Finally, to check if we're at the end, with indexes, we would check against some predefined size. For lists, we would either check for some sentinel node or null pointer. And finally, with iterators, we would check against a sentinel iterator or sentinel value. Are there any questions at this point? All right. So with this, we can change find to look like this, which is largely the same as before. We have a return type that is now uniform with the interface, and then we perform a check. We have a successor. We have a check to see if it's the value we're looking for, and then we return something in either case. The key difference here, and this is a bit of C++20 syntax, is that I've said that this is an iterator, and that is what's known as a concept, and that replaces the type name keyword, and it's a predefined interface that essentially checks to make sure that your type meets certain requirements, both syntactically and semantically. It has certain rules that you need to follow in order to make sure that you're compatible with this algorithm. Now, the real find has a bit more to it than this, but we're going to walk through this and then branch off before we would complete the find implementation. One question we need to ask is this iterator readable or writable? Now, the easiest way to explain this for now is that if we are trying to read from the iterator, then that would indicate that it is a readable iterator. That means that we can take a value from it. If it's writable, then it means we can write a value to it. And mutable iterators are iterators that we can read from and write from. And so because find is only ever doing reads, we need it to be a readable iterator. An iterator that is readable is known as an input iterator. And so this is what it looks like when we would like to use find with various types. So let's make this a little bit simpler. For a vector, it's simply a call to find where we take a beginning and an end, where the end indicates, okay, we have no more elements to search for. And then what we want to do is we want to check against the end. If we are at the end, then we haven't found anything. If we are at the end, so if we're not at the end, then we have found something. This is what it looks like for a list. It's pretty much the same. The only change really was the change in type. And this is what it looks like when we are trying to find something through a stream. And so we have taken the stream and wrapped it inside an iterator adapter, so that way it looks like an iterator and it works like an iterator, but underneath it's not actually a container. It's just an iStream. And a recap, if you wanted to see all three together again. Are there any questions at this point? Yep, one question.
Two questions. Why do you think it return the last value when you just finished searching and you haven't found anything?
So it doesn't return the last value. What it does is it returns a value that it returns something that indicates that it's past the end, or there are no more elements. We're at a pre-agreed element that is not actually an element. We're at a pre-agreed point where it says this is not a part of the sequence.
Yes. And why in these find functions you put the end of first 10 in this case? End of first 10, does that mean it's a 9? That means you never want to.
Can I answer this? Can I come back to this this question in a few slides' time, please?
Yes.
Thank you. No, that's fine. That's fine. So from this, we have. Let's say that we want to change things up a little bit, and we want to look through only the first 10 elements of a 100 element vector, for example. Now, we would need to make some sort of algorithm that mimics counting down from an integer from 10 to 0, and then stop searching once we've reached that number. But there are about 100 algorithms in the standard library, and if we were to do this for all of them, we would run into problems pretty quickly. So a nicer way of doing this is to provide a counted iterator, which lets us say that we are going through a certain number of elements, and we provide a type called a default sentinel, and this is a way of indicating that we have reached the end of a sequence and that there are no more elements. And the way in which we say we have reached the end is that we compare against the sentinel, and when the count is 0, then we know we have no more elements to look through. I'll give you a moment to digest this, but there's most of it's just boilerplate. Are there any questions at this point? Rachel.
Why are the equality operators friends?
The question is, why are the equality operators friends? And that is a really good question. The reason these are friends is it's not so much that I want them to be interacting with the implementation, but rather because when they are friends that are defined inside the struct, and this is very important, they have to be friends and they have to be defined inside the type itself, then they can only be found by what's known as argument-dependent lookup, which means that they're not names that are declared, and this has benefits for compile times. That's one of the huge advantages. Another thing is that you can't, they're not in any namespace because they haven't been declared. Does that answer the question? It's a very obscure rule that helps boost compile times.
Might ask you later.
That's cool. I'm not 100% sure on all the rules, but this is essentially the recommended approach at the moment until we get the spaceship operator. So what we have here at the very top, and you may not have noticed, is a default sentinel. And the default sentinel is a struct that's basically empty. It doesn't have anything to it. And we define all of our comparison operators for the counter iterator in terms of the default sentinel, because now we have something that's a common point of saying, basically, if you are equal to this, then you've met some rule that indicates that we have no more elements to look for. And so we can further generalize the find algorithm to take a sentinel and return, and indicate that we have reached the end through the sentinel. So if we have a counted iterator now, we pass in a default sentinel, and that's going to indicate, yes, we've reached the end of the range if we've exhausted the count. And this is how we would use it at the bottom. One thing I do want to note is that we have two return firsts in this implementation of find, because the type of, as opposed to what was in the previous find, which had a return first and return last. And the reason for this is because the type of the sentinel might not be the same as the iterator. The requirements are that it has to be something that is semi-regular, which means that it's copyable, default constructible, and it has to be equality comparable, which means it has an equal to operator and a not equal to operator with the iterator that we are passing in. Are there any questions here? Okay. Oop.
To find that equality operator, if you've got an entirely different type,
Yep.
that sounds a bit tricky. I mean, like, you need to know maybe some details about the type that you want to compare to. Stored in this sentinel value.
So if we take a look at the sentinel that we have here, notice that the sentinel's completely empty, and all the information is actually in the iterator. All we're saying is that when this rule that only the iterator knows about happens, then we've met the condition that the sequence is empty now. And really, the default sentinel is just a catalyst to say, have we met this condition? Does that answer the question?
I'll look into it.
Sure. And from this, we can now define a range. So a range is a type that has that represents a sequence of elements and has a beginning and an end. And so what happens is if we call begin, then it returns an iterator to the first element in the range. And if we call end on this range, then it returns a sentinel that indicates where the stopping point is. And I think this will go back to what you were asking about as well. So what end does is it doesn't return the last element, it returns something that indicates there are no more elements in the range. We stop once begin is equal to end. Does that answer the question?
Yep.
Wonderful. And we have what's known as an input range if we have a range that has an iterator that is also an input iterator. Are there any questions here? All right. And this is what find looks like when we have a slightly weakened version of find looks like when we have a range. Now the safe iterator simply means that if the type of R is an R value reference, then the type that's returned is not very usable. But if it's an L value reference, then we are able to interact with the iterator. So that's really just some protection against you passing in something that's going to expire at the end of the function call. Okay, so now let's move on to a different function. This one's called partition point. What partition point does is it looks for a point in a pre-partitioned sequence of elements that essentially no longer follows the rule. So for example, this sequence of elements is partitioned such that everything to the left of an element is less than or equal to everything to its right. 2 is less than 3, so this is still partitioned. 3 is less than 4, so that's why 3 is to the left of 4. We are going to look for what's called a partition point, and essentially that's where the partition stops being true for when I is no longer less than 3, and that happens when that happens at the first occurrence of a 3, because 3 is not less than 3, and this would work, but if we wanted to use partition point, you can see that partition point is defined in terms of find if not, and find if not is a cousin of find, which means that it works with input iterators as well. Which means that essentially, with input iterators, which work with streams, which are responsible for abstracting streams as well, we lose data. That means that we may potentially not be able to go back over and look at the elements that came before. So what we need is a way of strengthening or refining what an iterator is, what an input iterator is, if we are also allowed to go back. And this is known as a forward iterator. Which means that now we can go back and look at things that happened before, because presumably if we want to know when something stops being true, we want to go and look at all the things that came before that, or potentially things that come after it. We shouldn't make any assumptions on what the use cases are. Are there any questions at this point? Okay.
Is it called a forward iterator when it allows you to go back?
So forward iterator simply means that we are allowed to go over the elements. So that we're allowed to go over the elements multiple times. We can only move in one direction, and that's forward. But you're allowed to take a copy of a forward iterator, have that one be stationary, then move along with the original one, and then consistently walk over those elements. Does that answer the question? Cool. All right. Using a forward iterator, because it's a new shiny thing that we've been talking about, this is an implementation of a reverse algorithm with some debugging information. But it's incredibly slow because it has an n-squared implementation. And that's because we are not allowed to look backwards. We can only move in one direction. If, however, we make a new rule and say that we're allowed to move both forwards and backwards, then using what's known as a bidirectional iterator, then we can change it from being an n-squared algorithm to being a linear algorithm. Are there any questions at this point?
It depends on how you iterate through. I mean, if you have to go bidirectional, you still have to go, you potentially have to go for every single item, even if you go backwards.
So with a bidirectional iterator, we have, so the question is, wouldn't that depend on implementation of what, sorry?
If the iterator itself has to still iterate linearly, even if it's going backwards.
That would break the definition of what the predecessor function does, because the predecessor function requires that you are able to step back in constant time.
Okay.
Sorry, I didn't mention that. So one of the requirements of a successor function is that it can move forward in constant time, and one of the requirements of a predecessor function is that it can move backward in constant time. And so with this implementation, what happens is we start at opposite ends and work our way in until the two iterators are the same, and then we've met. So because we're swapping whilst we're walking into the middle of the range, we've got this in linear time. All right, here's some code that performs a shuffle. I want you to take a look at this very closely. This is a shuffle algorithm for a vector, but fresh deck function, which returns a fresh deck of cards, could return a list, it could return a deck. It doesn't have to be a vector. But the point is that it returns something that has a bidirectional iterator. I decided to benchmark this, and I had a deck size of 5 million cards. This shuffle algorithm took under 50 milliseconds for everything except for list, which took 11.5 hours to complete. So bidirectional iterators are, Simon, don't worry, this is on Twitter. So bidirectional iterators are not a good fit for a shuffle algorithm. Now, one of the nice things, can someone tell me what one of the nice things about vectors and decks are? Yep. So vectors are contiguous memory, decks not contiguous memory. But what's something that's nice about both of them? Cache performance, yes. And what does that also semi-allow? So can we access elements randomly in constant time, or near enough in constant time? So that's essentially what I'm looking for here. And that means that if we can access them in random, if we can access an element an arbitrary element in constant time, then we have what's known as and it's an iterator. Then we have what's known as a random access iterator, and this basically means that we can take a look at any other. We can go, instead of just being able to do plus I or minus I in constant time, we can do I plus 1,000 or I plus 1 billion and still get there in constant time. And this is what the shuffle interface looks like. Are there any questions at this point about the whirlwind tour of iterators that I've gone through?
Side question, was it double-ended queue? Did you say that was constant time for random access?
For random access, yes. So random access means constant time lookup.
I'm just curious how that works, because presumably it's the same rough implementation of a single forward queue, but it's just got pointers backwards.
So a deck, I believe, is implemented as a...
As far as I understand, it's a linked list of arrays.
Yes.
So it's a vector, which we divided into several parts.
Yeah.
And both of them, they have a pointer. So it's almost like vector, but so it gives you almost constant access time.
Is it like avatar?
I can't remember off the top of my head. Does that help answer the question?
Yeah.
Cool. Okay, now let's talk about a different programming language, because this is a C++ meetup. So I am very casually writing a Lexa for Rust at the moment. And one of the interesting things about Rust is that its strings are Unicode and UTF-8 encoded, which means that they're actually with the times, unlike C++. No, C++ is catching up. The escape for a Unicode sequence in Rust is to have a /u and then inside curly braces have up to 6 hexadecimal digits. Are there any questions about this? Okay. This is an implementation using a raw loop for detecting if a Unicode escape is correct or not. We start out with a few contracts. Because contracts in C++20 are not yet solidified, I've decided to defer to a macro that effectively has some rough implementation of contracts. And so what we're going to do is we're going to say this function only makes sense if we have more than 4 characters in a string, and the first 3 characters are \u and open curly brace, and the last character is a closed curly brace. And then we have essentially some computation that checks if the escape is correct. Now, can anyone tell me what this is aiming to achieve?
Checks if everything inside the braces is a hex digit.
Yep. So it checks basically if all of them are hex digits, and there is an algorithm in the standard library called all that does that for us. So what we can do is we can say that we have a beginning and an end, which we get from the standard library for free. We've essentially eliminated almost all the magic numbers that we had previously. And then what we can do is we can check that the distance is at most 6 digits, because what distance does is it checks that the number of elements between iterators is a certain number, and then we do our check with all of. Are there any questions at this point?
Yeah.
Joe.
Is there a mistake with this code distance?
Yes, there is a mistake from the next slide,
Oh,
because this slide is actually what's implemented.
I see.
As in, yes, this is the code that I have or had until this morning when I replaced it with the following slide. What we've done is we've taken the code from ranges, and we've essentially put our iterators, because we having just random iterators hanging around can lead to problems such as mismatching them or just having them as other names. We've put them into what's known as a subrange, which is essentially a non-owning type that holds a pair of iterators from the same range and allows us to reason with that. And now the code is significantly simpler than this slide here. And if you want to use what is potentially also going to be in C++20, then we can use range adapters, which allow us to change the code a little bit, but we can now reason about the code in terms of what we're actually doing. So here what we're doing is on line 10, we're saying that we want to take the first thing that comes after the curly brace, the first curly brace that we find. But really, because we know that the first curly brace that we find is going to be the third character, we can say that we're just going to discard the first 3 characters. And we know that the last thing that we want to find is a closed curly. So what we're going to do is we can say that the closed curly is, what we can say is we want to keep searching until we find a closed curly. And so we're going to take things until we find a closed curly brace. Now, this is a complete, this is a rewrite of what this code here is. Are there any questions at this point?
Usually the subranges, is there any check to say it's from the same range, or it just happens to be the same type?
So they have to be, so subrange isn't able to check that they're from the same range, but that is a semantic requirement. If they're not, then your program is allowed to break and you can't complain. That's just something that we can't check ever. Okay, let's get on to the final one, which is HackerRank's fraudulent activity notification problem. Now this has a rather simple problem definition. There's a bank that you work for, and it has a simple fraud detection system. And the way in which they detect fraud is that they look at the history of your transactions, and then they take the median for some previous number of days and double it. And if your transaction for a specific day is greater than in this computation here, then we're going to send you an alert. And for example, with this particular sequence of with this particular data, where the trailing history is 3 and the expenditure is as presented, on day 4, because the median is, which is the middle element of the previous 3 days, is 9, we double it, that's 18. 54 is larger than 18, so we trigger an alert. And then on day 5, the median is going to be 27, and doubling that gives us 54, but 52 is not bigger than 54, so there is no alert. Are there any questions at this point? No? Cool. All right, this is an implementation of the activity notifications problem. Give you a moment to let this sink in. And one thing I do want to point out is that what Victor was saying on the second slide, where we do want to sort a container, still happens. It's still here. What I'm going to continue on from here is by showing you how we don't always want to do this, and how we can work together with doing things on a full range and sometimes working on a partial range. Can I get a show of hands? Does anyone need a bit more time to digest what's on screen? 1, 2, 3, cool.
Let's replace all this dude.
Replace oldest is the meat and potatoes in the next section.
Oh, I see.
So we'll cover that in just a moment. All right, so to quickly go over this, what we're really doing here is we are going to look at some number of elements after the first element. So we're going to start at the 10th day of our transaction history that we're going to be looking through for triggering alerts, and we're going to work our way all the way to the end of the history that we have, and then we're going to check to see if our current value is more than double the median, and if it is, then we issue a notification. We then add the current day to the oldest sequence of days and remove the oldest day, and continue on until there are no more days. Now, based on what was being talked about in the previous section, can anyone suggest any improvements?
So if you're trying to get the median every single time you go into it.
So we need to get the median every single time because the days are changing every single time.
Okay, this is not very.
So trail is changing for every iteration. One thing we're doing here is on line 9, we're discounting the first D days pretty much after we've established what the trail is. So using range adapters, we can take the first D days and stick them in a vector and sort the vector. And then from there on, we can drop those elements, not worry about them ever again. Now, the data is still present in expenditure, and I'll show that in just a moment. What this means is that we are not going to look at that data anymore, so we can just discard it for our intents and purposes. These two implementations are equivalent. there any questions about what's on screen now? What we've done here is we've discarded a certain number of days. We've said that we are going to make the audited days the remaining days, and then we're going to essentially use a range for loop to iterate over things. And if you're like me, then you would want to stick that into lambda. But if we're going to put that into lambda, then we need to use something to join two of the ranges together. That is the audited days and the full history. So that way we can look back, because otherwise we wouldn't be able to look back. Are there any questions at this point? All right. But really, the interesting parts are here. So this all leads into what replace oldest means. So I'm going to walk through an example now. This is the sequence of data that we're going to look at. And the dark shaded elements are the ones that are going to be in the trail. And then on day 7, the grey ones are going to be, it's going to shift across a little bit, and day 8 looks like this, followed by day 9, and that's it. This is what days 1 to 5 look like. So this is going to be in our history. Can we find the median from this given data at the moment? No, why not? It needs to be sorted. So how about this? Now we can find the median's 3. That's fine. So now what we can do is, now what we want to do is we want to move to the next day, and the next day means we add a 6. All of a sudden it's no longer sorted. Now we could resort the data, but resorting the data is something that is going to be n log n in complexity for time. And we really only need to sort one element. So it should be better, if we're only going to be sorting one element, we should really be able to do it more efficiently. And there is an answer for that. Does anyone want to hazard a guess as to what that is?
I know there is an algorithm that will already sort of range shift forward to place.
Maybe just find the position and replace it with it.
Sorry, can you please repeat, and then can I get you to repeat as well, please?
I vaguely remember a standard algorithm that will work with a pre-existing sort of range with one will insert into the right place.
You were very close. Sorry, what was your one?
Find the one larger than this one and replace it with this.
Yep, so I think you've got the very last slide, actually. As in, you've just described the entire last slide. So we'll come back to your one in just a moment. So the answer is very similar to what you've suggested for this next slide, which is that we're going to rotate the first element into to the back. So the way rotate works is that we have what's known as an element that we want to have come to the front of the range, and then we pass in the rest of the range, and it's going to rotate everything until this element is now the first, and everything else will go to the back. And that's why 6 now is at the back. And then when we have 8, the exact same operation will work. It's just going to be rinse and repeat, so it's rather boring. What about 4? How do we get 4 into the correct spot? So if we go back, and I think this is what you were talking about just a moment ago. If we go back, we want to get 4 either before or after this element. And where 4 is currently going to be where 3 is next. And so what we do is we find the oldest element, which was a 3. We don't care which 3 it is, just a 3 needs to go. And then we override it with a 4, and that's what exchange does. It takes what's in current day and puts it in oldest, and then puts whatever was in oldest into old value. It does it in some sequence, probably not that order. And then what we want to do is we want to find, starting from the element that comes after the newly overwritten element, the first thing that is not less than the new element that we're going to be putting into place, and that will be 4. So that's why we have an arrow that's pointing to 4. And then we're going to rotate until that element. And what this means is, given the iterator-based rotate instead of the range-based rotate, we have a starting point, the thing that we want to have at the front, and then the sentinel, which indicates we're going to rotate until this point. And so we're going to rotate until 4, but we're not going to include 4 in what we're actually rotating. Meaning that we'll now have our 3, 4, 4, 6, 8 because we're only really rotating 3 and 4. So does that gel with what you were talking about? Cool. Are there any questions at this point before I move to the next slide? Yep.
How do you work out the oldest value?
So the oldest value is worked out from, so we look at this and
Because it's all sorted,
so that that's why we have the 3 here. So that's why we have the trailing data and why we need to look back at what the expenditure is rather than just forgetting about that entirely. We still need to look back, and what we're doing is we're saying the oldest value is a 3. It doesn't matter which 3 it is, just as long as we get a 3, then that's okay. And we want to get rid of the first 3 because that's just going to be the easiest for the implementation. Does that answer the question? So we look at the top sequence of elements and we see that the oldest one is a 3. And then we look at the bottom one. So we then do the right in the bottom one. Does that make sense?
kind of just that it looks like the old values too. But
Yeah, what do you mean by the old values 3?
That could be a slide mistake. I will update the slides and get them to you. But yes, pretend everything that I've just said was 2, not 3, and this actually magically says 2. And this is what the implementation of replace oldest actually looks like. So what we do is we do the bit that I was saying before where we find the something that matches the oldest value. And then if that is less than the oldest value, what we want to do is we want to start rotating. So if the oldest value is less, if the new day is less than the oldest value, then what we want to do is we want to start rotating from that element until we reach the end. So that way it gets to the front. And otherwise, we want to rotate in the opposite direction until the largest point, so that way it gets to the back. Are there any questions about that? Yep.
Just kind of wondering about the underlying sort of structure of this, what's called the trail. Like how we do all these rotates, are we shuffling things along, or is it updating pointers?
So we're shuffling things along. It's a linear algorithm. And this is actually one step of an insertion sort, if that helps make things a little bit clearer.
Yeah, I think so. Yeah, insertion sort of like a contiguous.
Yes. Yes, that's important because it's a vector. Yes. I think I've just doubled a slide. Oh, right. Okay, yeah. So the difference between these two slides is that this one is the iterator-based one. And that works with the original implementation that I showed. Whereas this one here works with the range-based implementation. So only 2 lines actually change, which are lines 3 and 4, to not use iterators, basically. So in conclusion, what I'm trying to communicate here is that algorithms are a powerful way of describing what you want to achieve, and range abstractions help you do that. But they don't work in isolation. The underpinnings of a range are iterators, and from there, when moving forward, it's important to consider that ranges and iterators do work hand in hand, and that they are used to help describe what you're trying to achieve using algorithms, but none of them can actually be used in isolation. I'd like to thank you for your time and open the floor to any questions.
That's what we talked about. Sorry, you mentioned
What were your favorite algorithms?
My favorite algorithm is probably rotate, followed by accumulate. Accumulate is something that I find myself using more often than I'd like, and I'm very sad that it's not going to be updated in C++20. That's also on me because I'm the one that said I would look into getting it updated. Yep.
Yeah, so the question I just had about the insertion you said in your time because it was a vector. If you use so if the whole data structure you were trying to do that fraudulent test on was a list, say,
Yep.
then the underlying iteration kind of worked on a list as well. Sorry.
Yes, it would work. So the question is, if this was instead of being a vector, would it work on a list as well? The answer is yes, it would work because lists. I think I'm going to get to what you're actually wanting me to answer in a moment. So lists in C++ are bidirectional ranges, which means that because rotate, I think takes a forward range, it's compatible. But to answer what I think you actually asked me, not what I think you asked me, but what. So if I understand, if I understand the actual words you said, it's more a case of can you just rearrange pointers? Is that what? Yeah. Okay. Cool. I did look into that. I couldn't work out how to do it with list, which is why I didn't say, well, you could just do this instead. If I had worked out how to do that, then perhaps this example would have been replaced with a different example altogether. But rotate doesn't do that, or at least an algorithm-based rotate can't do that. It would have to be a list.rotate instead. Does that answer the question?
So, yeah.
Okay, cool. Are there any other questions? Ben?
Is everything you showed us here going to be in C++?
So if I get my way, or if I and others get our way, the idea of two vector and drop and the take while that I mentioned many slides previously. This is bidirectional, not random access, so I can't just jump in constant time. Those will also be in C++20. Those ones at the moment aren't in C++20. They're on the short list, but it comes down to do we have enough time to review the proposal to get it stamped. So essentially, it's a case of is there enough time to review the wording and we'll go in. If these things do get prioritized, then they'll be in. Otherwise, it'll be a case of well, it missed it by that much. And unfortunately, zip didn't make it in at all. But that's available through Range v3, which is now in version 0.5, and it is compatible with MSVC 2019. Is it also 2017 compatible?
With patches.
With patches, okay.
Would it be pretty seamless to go from using Range v3 to stood ranges?
Using Range v3 version 1.0 beta, so if you use the beta branch, it will be much easier to change across. I haven't done it for a while. I have a project that that can change across. It used to be a bit of a pain, but Range v3 is being in the process of being updated so that way it's standards compatible as opposed to being something that standards like. So I think the answer to your question is once 1.0 ships, yes, we're not quite at 1.0 yet. Simon?
Roughly how much, percentage-wise, how much of Range v3 made it into
The question is percentage-wise, how much of it of Range v3 made it into C++20? The answer is we barely scratched the surface. So there are a large host of range adapters that that didn't make it in, and there's everything from the numerics library, which is still to be researched. And then the range adapters that we have at the moment, this view, for example, doesn't actually do any computation. It's lazy. It needs to be asked to do work, which is what this 2 vector does. It says, hey, I want you to take the first D elements. But if we hadn't put that 2 vector there, then it would just be an object that did no work until we asked it to. There's a whole class of range adapters called actions, which eagerly do things, and those haven't even been designed from a standards point of view. So those will hopefully be in a future version of C++, but we're hoping C++ 23. That doesn't mean it will actually be C++ 23. Are there any other questions before I pass back to Joe? All right, well, thank you for your time, and